welcome to the course Advanced Reaction Engineering. So, we were discussing non-ideal flow and dispersions models. So, today we will discuss dispersions models. In our previous class we have discussed the when dispersions is there. So, how that would affect the overall performance of the reactors. So, conversion concentrations that will change. So, based on that we have derived dimensionless equations. So, that is when flow and dispersion is there inside of the reactors. Let us say this is the reactor. So, here whence any fluid is passing or entering inside of the reactor. So, and we injected a tracer, pulse injections of the tracer, that is the pulse concentration or tracer test is there. So, there's normal flow would be there, means along these directions of that molecules, tracer molecules, and with that diffusions would be there. So, with that dispersions or diffusions would be there. So, once we know that means dispersions is there, so then we can we have developed these equations, that is the second order differential equations, dimensionless forms we have derived for the tracer test, okay, from the tracer test or tracer experiments. So, in these experiments these equations we have to solve using some boundary conditions. Once we solve, so what we can get? We can get Peclet numbers, okay. So, Peclet numbers, so that we can get by solving equation 3. So, for that we have to use some boundary condition that we will discuss. So, now means what is the purpose of this? Means to find the Peclet number or dispersion number or dispersion coefficients using this. For that we have to use tracer test. Tracer test, from the tracer test what we can get? Tm, tau, sigma square, these are the things or parameters we can get from the tracer test or residence time distributions. Once we do that, so these are the things we can get. These are the components we have to use to find out the Peclet numbers basically or dispersion number. So, once we get dispersion number or Peclet number from the tracer test, then we can implement for our reacting systems or when reactant is. So, here reactant is passing, see here tracers would pass, okay. So, tracer T would pass, here reactant would pass. So, when reaction reactant is passed through the reactors, these reactions would take place. Let us say this is first order reactions. So, with flow dispersions reactions is there. So, in that case we want to measure final concentration or outlet concentrations or conversions. What would be? Means using these models we want to predict, means with the help of tracer test, dispersion tracer test, we can get these dispersion numbers, will get that dispersion numbers we can use here. This is these equations we have derived or second order differential equation for these systems, okay. For these systems we can get these equations, okay, and when flow dispersion is there, this is the second order differential equations. So, here here this unknown parameter is the Peclet number. So, Peclet numbers means we cannot means derive directly, for that we have to take the help of tracer test. Once we know the Peclet number to find out, we need this, and then that we can substitute here or dA or Peclet numbers, whatever we are getting from tracer test, that we can substitute here, then this equation easily can solve to find the outlet concentrations or conversions that we can predict with that help of these things, okay. So, here's these two equations if you want to solve. So, we need some boundary conditions I said. So, how these boundary conditions is coming? So, the dimensionless forms equations we are solving. So, the boundary conditions whatever we develop, that also should be boundary dimensionless forms, in the dimensionless forms that you have to use, okay. So, here's the boundary condition, there are two type of boundary conditions. So, one is closed boundary conditions for the vessels and another is the open boundary conditions for that vessels, okay. So, these are the things two boundary conditions we will discuss. So, when diffusion is there, so first we will discuss closed boundary conditions to find out dA, means on the basis of tracer test we can means these boundary conditions we can implement or we can apply to solve equation 3. Once we solve, then we can get dispersion number or Peclet numbers that we can use for the second equations or equation 6 to get dimensionless concentrations psi or Ca whatever that we can get, okay, when reactions is there or we can predict the conversions. So, in the boundary closed vessel boundary conditions, So, here there is some assumption is there. So, there is no dispersions or radial variation in concentrations. So, when molecule is moving from along the directions, flow directions of the reactors, axial directions. So, there is no dispersions or radial variations in concentrations we assume, and either upstream or closed means this here's this is the flow or bound, when this is the tubes you can consider, through that fluid is flowing along these directions left to right. So, here we are considering at point z equals to 0 and this is z equals to L, two different points inside of the reactors, or in the reactors we can consider at z equals to 0, z equals to L. So, if and this is called upstream and this is downstream, you can say both are closed, means when this part is closed and this part is closed and molecules injected inside of the reactors. So, then what would happen? So, once it is cross this points z equals to 0, then diffusions might be there. So, outside of that or before that z there is no diffusions, means d equals to 0. If there is no diffusions, diffusion coefficient should be 0. Here also when z equals to L leaving, means after from these points molecules when leaving there is no dispersions. Okay. So, before entering here and before after leaving these points there is no dispersions. If dispersion exists, that is in between that z equals to 0 to L, within that dimensions we are assuming that there is dispersion. So, therefore, dA greater than 0. Okay. So, we are considering this is the closed vessels boundary conditions to derive. So, this is the conditions we are considering. Okay. So, any fluctuation or deviations or dispersions of concentrations of molecules is within this boundary. Okay. Z equals to 0 to Z equals to L. So, before that and after that there is no dispersions. And second one is there open vessels. So, this is closed vessels boundary conditions and this is open. So, dispersions occurs both upstreams and downstreams of the reaction systems or reactors. Okay. This is the entrance, this is the exit. So, before entering here there is dispersions, after leaving the reactor at z equals to L point there is also dispersions, and in between that also there is dispersion. So, here dispersions is there, here is also dispersions, and in between there is also dispersion. This particular assumptions is or this type of boundary conditions we have to develop. So, here these are the assumptions. So, here this is for open vessel and this is called closed vessel systems. Okay. So, here only here dispersion is there and rest of the part there is no dispersions. Here everywhere you can see dispersion is there. Okay. So, here see z equals to 0. So, z equals to left hand side just very close to that 0 minus, and here 0 plus, z equals to just right. So, this point is 0, but close to 0 and after means this just left hand side and this indicate right hand side, 0 minus and positive indicate that. Similarly, for z equals to L, L minus, L plus, L minus indicate left hand side of the z and L plus indicates just leaving the reactors. Okay. Just entering O minus 0 minus, that indicate before entering of the reactor. So, O plus to L minus, within that this type of closed vessels dispersions exist. So, therefore, here the concentration Ca C, it is horizontal, straight line is there, Ca not this point everywhere up to this is same, but once it is enters this concentration is changes due to the dispersions. So, here concentrations we are expressing in terms of Ca 0 plus, okay, whence it is crossing 0 plus, okay, and here it is just before entering. Okay. So, here at this particular point dispersion is there, here there is no dispersions. Okay. So, at this conditions. So, here at z equals to L you can see once it is leaving the reactors Cal plus. So, there is it is straight line, but here it is like this, means concentrations there was dispersion, therefore, up to this Cal minus concentration changes, means dispersions is there. So, at this particular point when z equals to this particular point, concentration gradient dCA by dz at z equals to L equals to 0, and at this particular points we can say means just crossing z equals to 0, 0 plus at this particular point concentration equals to this concentrations plus inside there is dispersion. So, if we sum up that, so at this particular point the concentration is this, and at this particular point there is concentration gradient equals to 0 at z equals to L. Okay. So, now this is the way the molecule is moving. So, you can see here there is no dispersions, just crossing, here just dispersion has started. Okay. So, this is close boundary conditions we will discuss, and how to derive the boundary conditions, equations for boundary conditions, and then that we have to convert into dimensionless forms to solve that equations we have derived. Okay. So, at z equals to 0 molar flow rate is this, at z equals to 0, here at this particular points you can see at just z equals to 0 minus 0 plus within that particular points. So, at t time, okay, molar flow rate at z equals to 0 is this. Okay. And whence dispersions is theirs. So, this molar flow rates are these equations we have discussed at the beginning. So, molar flow rates due to the convections plus diffusions is this. So, these equations we can implement or substitute this Fa here and here. Okay. So, 0 minus T and 0 plus T, that way we can substitute. So, when at this particular points I said there is no dispersion, so then this part we can eliminate. So, therefore, at 0 z equals to 0 minus u a c c a 0 minus, this part is eliminating, only this part is lefting. So, therefore, in the left hand side it is remained there. So, since there is only convective flow is there, there is no dispersions, just crossing the 0 0 plus at this particular point. So, these boundary conditions, these concentrations or molar flow rate of component A is this, and at this particular point is this. So, here this molar flow rate means this is for diffusion, this is for convections. Okay. So, if we multiply it by AC, AC is there. So, this way totals would come, and here 0 plus z equals to 0 plus. So, this is at z equals to 0, the boundary conditions is this. Okay. Did you get my points or not? So, this is at z equals to 0 for closed vessel system. So, at this particular points, so we are elaborated here, and based on that mole balance we have done at this particular points at t time, and then we are substituted these equations, we get this. This is the boundary conditions when z equals to 0. Okay. So, similarly, means these equations, if we means C A naught, C A 0 minus, C A 0 minus, C A 0 minus is this, means when just molecules is entering or treasures initial concentrations you can say. So, when just high concentration or component is there, so here concentration is high and just entering in the reactors. So, C A 0 minus we can say C A 0, but here we cannot say C A 0 plus equals to C A 0, since there is diffusion. So, concentration would be different. So, therefore, at this particular point C A 0 minus, that we can substitute this, and other points in the right hand side whatever the things are coming. So, after substitution this and simplifications we can get this. These equations we are converting into this equation 1. So, is it okay? So, after means first we considering this particular point z equals to 0 minus z equals to 0 plus molar flow rate we have considered this F t equals to this. These equations we are substituting here left hand side and right hand side. In the left hand side this component is not present, since there is no diffusions or dispersions d equals to 0, therefore, this component is 0. Okay. So, then this component convection flow or molar flow rate is left, that part is there. In the right hand side only this is there, and here left hand side actually it is coming C A 0 minus equals to rest of the terms. Okay. These are the terms remains here. Okay. And here C A 0 minus equals to C A 0, we are substituting by Ca0 equal to what are the terms which remain there. So, this equation is coming from there. So, this equation once at z equals to 0 is called Dankwardt boundary conditions. Okay. So, now closed vessels at z equals to L point, z equals to L point. So, that we have to consider. So, at z equals to L point means at this particular point z equals to L, at this particular point here also dispersion is 0, there is no diffusions, just leaving the reactors, or else you can see here at this just immediate it is almost 0 here, and then leaving the concentrations remain the same. So, here dimensionless gradient concentration gradient equals to 0 you can say. So, at z equals to 0 no concentration gradient is there for the tracer component, or you can write this in terms of component A, Ca0 L minus equals to Ca L plus, okay. Or you can say delta Ca by delta Z equals to 0 at this particular points, okay. So, at Z equals to 0 Dankwardt boundary conditions is this, and at Z equals to L this is equals to this, okay. These are the two boundary conditions we obtain, okay, at Z equals to 0, at Z equals to L. So, these are the two boundary conditions we have. So, these two boundary conditions is not dimensionless forms, we have to express this or convert that into dimensionless form, okay. So, at z equals to 0 first let us do these equations was there at z equals to 0, that is the lambda equals to 0, okay. Z equals to 0 equals to lambda would be 0, if z equals to 0 means lambda equals to 0. So, then and psi equals to Ct by Ct 0, that or Ca by Ca 0 we can say. So, these equations would be converted into this, okay. So, at z equals to 0 if these equations means psi equals to dCa by dCa 0 you can say, okay, and lambda equals to z by L, okay, at here lambda equals to 0 at z equals to 0, okay. So, these equations we can express in terms of this, okay. We are converting equation 1's Dankwardt boundary condition in dimensionless forms, and equation 2 that also we are expressing at z equals to L, z equals to lambda equals to z by L, when z equals to L lambda equals to 1. So, lambda equals to 1 then d psi by d lambda equals to 0. So, this is means two boundary conditions, means this is 1a, this is 2a we can say. So, these are the two boundary conditions from equation 1. So, we got equation 1, and from equation 2 we are getting equation 2a. These are the two boundary conditions we derived, okay. For that we can express in terms of for tracer as well as reactant component. If it is tracer we will express Ct, if it is reactant we express Ca. So, psi we can express when tracer Ct 0, when psi equals to reactant Ca by Ca naught, that way you can write, and similarly lambda equals to z by L, when z equals to 0 lambda equals to 0, when z equals to L lambda equals to 1, okay. So, this way two boundary conditions we have derived. So, now equation 3 we have to solve using these boundary conditions. These two boundary conditions we have, if we solve this analytical these equations, then the analytical solutions would come this, okay. And from the residence time distribution functions, that mean times and variance we can get for first moment and second moments, this we can get from artery study, okay. So, here's these equations once we have, we can solve these equations, means from the tracer test we can get this component. If we know tracer test means T, C, E T, then we can similarly we can mean times and variance we can find out. So, by that way this we can find out, okay. So, means from the tracer test as we did in our previous class that we discussed. So, variance we have to find out and mean residence time distributions or TM we can find out. So, once this two numerical value known, so then we can substitute here and then by trial and error by using any nonlinear equation solvers, Peclet numbers we can get. Peclet number equals to UL by dA. So, from here once we know Peclet numbers, the whatever the Peclet numbers will come, that we substitute here. U and L superficial velocity and length of the reactors if you know, then dispersion numbers or dA we can find out. Okay. So, one equations we are solving considering these boundary conditions. So, details are not given here. This equation now if we solve using those boundary conditions, this analytical solutions we can get, and first we have to calculate Peclet numbers, and for that we need mean residence time and sigma square, that is the variance from the RTT data. So, once we know, then see here sigma square Tm squares we can substitute, then by trial and error or by using nonlinear regressions we can find out Peclet numbers. So, from these equations once we know Peclet number, then dispersion numbers we can say. So, from these equations if means we have solved and we have got the dispersions numbers. So, once we solve this we can get dispersion number. The dispersions numbers might have some value. This after solving these equations with boundary conditions we can get some value, let us say 0.002 dispersion numbers we are getting from that particular treasure test. Peclet number we found, and from the Peclet numbers we can found a dA dispersion numbers or dispersion coefficient, that is very 0.002 for that system. Treasure test means whatever the reactors we have derived design, that reactors there we have conducted the treasure test, and once we have conducted the treasure test, the final equation analytical solutions or these equations we have obtained. Here sigma square Tm squares we find out from this treasure test, we substituted here Peclet number we get, and once we get Peclet number, from there we can get dA. So, dA is very low. What dA actually signifies? dA may be very large, maybe 0.2, dA may be 0 or dA may be infinite. So, any numbers it may be. So, if may be 0 there is no dispersions, if dA has some value it means there is dispersions. Okay. So, indicate this actually indicates whether there is a dispersions, means the reactors we have derived or we have fabricated or designed, whether there is dispersion is there or not. So, if dispersions is there means the reactor is not behaving ideals. So, then from there we can see the natures of the here's effluent dimensionless effluent concentrations in the y axis we are putting psi equals to Ca by Ca naught or Ct by Ct naught, and dimensionless times if we plot, and if d by UL equals to 0. So, then Peclet numbers would be infinite, inverse of that. Okay. So, then if it is 0 then it indicate the reactor is behaving like a plug for reactor. Then the dimensionless concentration and times if we plot, it would be like this, or you can say it would be like this. Okay, dimensionless concentrations and dimensionless time theta, that is T by tau if we plots. So, whence d equals to d by UL equals to 0. So, then it would be like this. Whence d by UL equals to infinite, it means there is dispersions exist, then Peclet number equals to 0. So, in that case it would behave like this. So, it means this is PFR indicate and this is indicate mixed flow reactors or CST reactors. Okay. So, here d by UL equals to infinite. Okay. So, in between any number, so some intermediate amount of dispersion, small dispersions is there, so large dispersions here is there. So, this way it indicates, this curve signifies this, means whether there is dispersions or not. So, if the nature of curve is like this, so then we can say some dispersion is there. If it is like this, we can say some dispersions is there. If it is like this, there is some dispersions is there, means up to that dispersions is there. So, this is the means whatever the dispersion scope means dimensionless concentration and times we have. So, if we express that, so this way we can express it. Okay. So, always means small dispersions or large dispersions, this is just means a value, numerical value, it signifies or dispersion. So, whether there is or not, means when means through the treasure test we can get this value, and based on that we can assume or we can correlate that, we can say that or conclude that there is some dispersions is there in that reactor. So, accordingly when we conduct the reactions for that particular reactor, using that reactors, reactant is flowing. So, reactions would be there, at the same time some extent of the molecules, means the reactants A components will disperse. So, up to what extent it is dispersing or non-ideality or dispersions is there. So, using this dispersion number, therefore, the dispersion number is very important. So, why we are going to find the dispersions number. So, dispersion numbers or Peclet number, either ones we can find out from our treasure test. So, once that numerical value we are able to know, so then easily we can conclude that the reactors is up to what extent it is dispersed or dispersions is there or not, or non-ideality is there. Okay. So, now we can summarize. So, we consider case A and case B, that is for treasure and that is for reactants. Two different design equations we have developed, and these design equations are this means dimensionless differential equations, second order differential equations we have derived, and these two equations we have solved considering boundary conditions, closed and open boundary conditions are theirs, and first closed boundary conditions will derived, and then in the form of dimensionless forms we have expressed that, and then that implemented or applied to that equations we have developed. These equations here, this equation we have solved to get Peclet number or dispersion number. Okay. So, boundary conditions, closed vessels boundary conditions we have discussed, and open boundary conditions that we have not discussed, that is discussed later. So, closed boundary vessel boundary conditions we have discussed, and based on that this we have discussed at z equals to 0, and this is at z equals to L's, and then when it is expressing in terms of dimensionless forms. So, at z equals to or lambda equals to 0 these equations, and lambda equals to 1 this equation we have got or we have expressed that boundary conditions, and then these equations we have solved with the help of these boundary conditions. So, we get these analytical solutions, and analytical solutions we can solve once we know RTT data, then we can get Peclet numbers, and Peclet numbers we can convert that into dispersion coefficient or TA. Okay. So, dispersion numbers, so that way you can express, and how that dispersion number signifies and what it signifies, that we have discussed, and easily from these curves we can say that. Okay. So, thank you. So, today is up to this, and next day we will discuss something else. Thank you.